So good afternoon and welcome to today's general lecture on periodic table. It's 150 years since periodic table was first published, and that is the reason why the United Nations has declared that 2019 will be celebrated as the year of the periodic table. And if you look at this website, go to their URL, you will notice that they say the reason we are celebrating this is because the development of the periodic table of elements is one of the most significant achievements in science and has had a uniting effect on various disciplines such as astronomy, chemistry, physics, biology, and other natural sciences. And they mentioned that the reason we are celebrating this year as the year of the periodic table is because in 1869, Mendeleev published his first periodic table in this year. Coincidentally, of course, this year also happens to be the 150th birth year of Mahatma Gandhi. So there are many, and they also mentioned that, for example, why this is very crucial, the periodic table, how it has enhanced. And also, if you notice, the most four recent elements, 113, 115, 117, and 118, were added to the periodic table, and this happened a couple of years back. So just to kind of once again emphasize why do we want to celebrate this, apart from the fact that of course there is Mendeleev's contribution in organizing the information that was there helped a lot, but also in a sense this celebration is also to show the importance of science in general and chemistry in particular, and to allow people to be attracted towards science and show how this development of periodic table has had a long impact on science, and therefore can we use this occasion to attract young students to chemistry and physics in order to ensure that the next generation of scientists, engineers and innovators can come to this field. Of course, needless to say, my periodic table has had a large impact, particularly with fields in medicine and materials. So this is their, they have come up with this sort of logo. You have 1869 to 2019. This is the original version of the Mendeleev table, and this is the modern version that is there. And if you look at periodic table anywhere, we should have here somewhere. Normally every lecture hall would have a periodic table. So you notice certain things depending upon your interest. So this particular periodic table, you have, there are color codes. For example, the ones in Pekka, which are over here, are elements that are known to humans since antiquity. So for example, we in India know about gold for a long time. We have been fascinated with gold. I think it's several since thousands of years. We also know about iron. For example, the iron pillar in Delhi, it's actually an iron pillar, not a steel pillar, and it is still, it hasn't been rusted because of the technology that we knew how to keep iron from rusting even in an environment like Delhi. And there are many other elements that we knew. Mercury, for example, is something that ancient Indians knew and used it sometimes wisely, sometimes unwisely in medicine, and so on. And also there are elements that are known since 1800s. There are elements known since Mendeleev and known more recently. You can also look at the periodic table from the point of view of what we can do with it in terms of what chemistry can be anticipated from it. So for example, you immediately know that here are the electropositive metals which love to lose an electron, and you have electronegative elements which would love to gain an electron. You have transition metals with variable oxidation states. You have lanthanides with deeply buried f orbitals, and so on. So a tremendous amount of information is packed into this table, and therefore very rightly we are celebrating this the genesis of this periodic table. But if you look at the first table that was published by Mendeleev, this was in 1869, and actually this particular version was published in a very obscure journal that Mendeleev and a few other colleagues have themselves started, called Journal, and this was in Russian. And Mendeleev, of course, very quickly realized that if it is going to be in Russian, then it is not going to really go anywhere. So he got it translated and published in Zeitschrift Chemie, and the title of that particular paper was on the relationship or the properties of the elements to their atomic weights. And you notice here, this is somewhat different to the periodic table that we are used to, but there is a certain order that is present over which I will come back when I discuss about Mendeleev's table in a little bit more detail later. But already this is a very advanced version of knowledge in terms of the chemical elements and their organization, and has really helped a lot in terms of moving chemistry forward. So there are several key players. It is not that Mendeleev alone did this. You have Mendeleev, of course, deserves a lot of credit, but also simultaneously there are several people like Lothar Meyer who had done this work, and Moseley, who contributed a lot to this but died very young due to unfortunate circumstances. And there are pioneers before Mendeleev who actually kind of established chemistry the way we know today, Lavoisier and then Dalton, and of course the modern era, we have T Seaborg, who has extended the periodic table and put a place for lanthanides and actinides and so on. I have missed some names, some important names are not there in this picture. There is Berzelius who is missing and some others, but it is simply a subjective choice of what I think more important. Let's start with the elements, because this is a periodic table is a table of the chemical elements. Now, what are elements? Of course, people have been worried about this for a long time. The Greeks have worried, the Indians have worried, and very similar conclusions in terms of what the elements were according to the Greek and Indian philosophy. So the Aristotle and Plato school said that everything is made up of one or more elements: earth, water, air, fire. And of course, the Indian philosophy continues to state that the basis of all cosmic creation are the Panchabhuta, Akasha, Vayu, Agni, Apas, Prithvi. So there is a commonality in thinking, and this has continued for a long time. And we come to a stage, I have skipped a lot of history, although this is a talk about history of chemistry. I'll come to a stage where we have these people who are the alchemists, who were experimenting with everything. And my fellow chemists, when I talk about this, these are our ancestors. So chemistry, unlike physics, was not really motivated by very noble goals. We had started with actually very utilitarian, and if you can use the word, very greedy sort of motivations. We wanted to convert everything into gold, and therefore that was our beginning. And so you can see that even now, for example, when we speak, perhaps some of this past rubs off on us, and therefore my apologies to my other colleague scientists, this is our past. So we start off with this very beautiful painting of the Alchemist, and incidentally the Alchemist is actually the Egyptian. It is the that is how the word alchemist comes from, and most of the very ancient chemistry was actually carried out in Asia and in Egypt, and was then taken to Europe. So this painting actually shows an alchemist who is taken aback at this phosphorescence that he is seeing. And this is a little gross, but I have to share with you what alchemists have done. So what this person, this is, we come to one of those alchemists, there are several. One of the alchemists is Henrey Mosely, and all of them were in search of this philosopher's stone. They wanted to transform anything into gold. That was the basic objective. So Henrey Mosely, of course, looked at the human excretion, the urine, and thought that the yellow color of the urine has to perhaps do something with the hypothesis that maybe there is gold in this. And so he set out a laboratory. Now he happily did not have to do any job, because he married wealthy wives. His first one passed away, then he quickly married a second person who also had a lot of money, and therefore could indulge in this sort of an experiments. So he discovered P4, phosphorus, during his experimentation. He did not discover that urine had gold, but he did discover phosphorus, and the way he did was he processed urine. So he had, for example, a typical, we could call it experiment or a process, consisted of heating 5,500 liters of urine. and concentrated this, and the picture that you saw before was actually at a stage of concentrate when this concentrate suddenly, perhaps not as dramatic as this painting showed, but suddenly it was phosphorescent. And of course he was really amazed that there is something that you are getting from this. He could not make much money out of this, unfortunately, but he could sell the process, and this process reached Robert Boyle. Now Robert Boyle was also an alchemist, apart from many other things. Boyle's laws we have read in the school and so on, was many things, but he already was looking at alchemistry perhaps with a little bit of skepticism, and he wrote a book, and his book is called the Skeptical Chemist or Skeptical Chemist, and he starts to question about some of this earth, water, fire, air business, and this book actually contains all that Robert Boyle thought about his early theories. And also very interestingly, apart from many other things, he also was a director of the East India Company. So he was involved in this early East India Company, but he was a little bit more in terms of chemistry, had more knowledge. He refined the process of P4. Now he had a reaction, he added silica to this, and of course the actual reaction now we know is this is basically what's happening. You have the phosphate which is getting reduced to the carbon in presence of silica, which takes out this sodium silicate and you generate P4. So more recently, that is last century, we had in 1970s, actually people realized why is P4 giving off this color, giving off this photoluminescence. Actually it's chemiluminescence. So it actually generates two chemical entities, H2O and P2O2, which emit light. So we know now why does it actually give light. Okay. Now let me kind of come to this, I'll take off from Boyle's skepticism. And the skepticism started by looking, is air an element? Is it a single entity, or are there more entities in it, right? Now, of course, this question is so obvious to us, but just put yourself back 300 years back and imagine yourself to be somebody pursuing this question. It's not so trivial, and actually, it's quite amazing when you go through the history how they could deduce so many things with the type of experimentation that they had. So we'll start with Joseph Black, and Joseph Black was a person in England, in perhaps Scottish, in 1750. So he had limestone and acids. He had limestone, added acid, then he got air, and he found that this air that he had was denser than the normal air, and also it did not support life. So the typical experiment that they had for not supporting life was they would have a bell jar, have a mouse under the bell jar, stick this air that they were experimenting with, see whether the mouse lives or dies and how quickly it does. And then, so the conclusion was this new air did not support life. And so this was called the fixed air, which we now know as carbon dioxide. Joseph Priestley, who was at that point of time in England, later he moved to, as you know, the United States, and so he bubbled this fixed air in water and found out that this water, so bubbled with the fixed air, had a nice tingling taste. And indeed, therefore, one can call Joseph Priestley as the father of the modern soda. And indeed, if those of you who have gone to Germany would realize that they don't drink normal water. Most of them buy their water and call sparkling water, which is this carbon dioxide in water. And he published this, which is actually accessible. Even now you can take this particular paper in Philosophical Transactions. So, coming to this air being a single element, then Rutherford, Daniel Rutherford, so what he did was he burnt materials. Then he already knew that there is a thing called fixed air, and it was known by this time that this fixed air can be absorbed by potash, and then what was remaining also asphyxiated mice. So he called this air noxious air. So you can see the unraveling of what was an element air. You now know that there is a fixed air, then you know that there is a noxious air and so on. And very quickly, Henry Cavendish found out that there is a flammable air, which is hydrogen by the action of acids or metals. And all this action took place in England. So like many areas of advancement in science, the advancement in chemistry was to at least for 50 or 60 years thwarted by this hypothesis called the Phlogiston Theory. So there was a theory which everybody believed that the hypothesis is any flammable material had a substance called phlogiston. So when these materials burn, it was released during combustion. So for example, if a candle burned, the phlogiston was transferred to the surrounding air, and when the entire phlogiston is transferred to the surrounding, the flame went out, and if the air became phlogisticated, it cannot support combustion, and so on. So this was a theory that was there, and actually many then very, very prestigious people believed in it, including Joseph Priestley. So for example, Joseph Priestley said that metals have phlogiston. If they are heated, they give up phlogiston to be what they call as calx, okay, which we now know as metal oxides. So, and similarly, they related to breathing. Breathing takes out phlogiston out of the body. So you place a mouse in a container. So the air in the container does not accept phlogiston, then the mouse will die. So this was the philosophy. And Priestley, who was the person who actually discovered oxygen, and he called it the vital air. His experiment consisted of using sunlight. Here was mercury calx, which is HGO. So when you take sunlight, concentrate it to the lens and then shine it on the mercury oxide, then this is one of the cleanest reactions among metal oxides. This happens to be one of the reactions where this decomposes and you get the metal and the oxygen. So you can see that this oxygen is generated, and he found out it's much better than normal air, and mice lived longer and so on. So he called it the vital air. Now at this point of time, of course, even in Europe, communication wasn't excellent, but it was definitely better than other places. So Priestley had an invite to the French Academy of Sciences, where of course the nobility and the leading scientists of France were at the dinner table, and Priestley was explaining his vital air theory in French, and this was picked up by Lavoisier, so claimed the English. So this is not completely kind of authenticated, but it is one could accept it because Priestley had discovered this oxygen. Now Lavoisier's entry actually demands a little bit of time in terms of describing him, because he can be considered very rightfully as the father of modern chemistry. Now here is a very beautiful painting of Lavoisier and his wife. His wife had a very important role to play in whatever experiments he had done, and indeed modern historians of science believe that had she been there in today's world, she perhaps would have been as successful scientist as Lavoisier in her own right. So what did Lavoisier do? He transformed chemistry from this alchemy and a qualitative practice into a quantitative one. He wrote the first authoritative book on chemistry, which was translated in all European languages, including English, Elementary Treatise of Chemistry. He defined an element, a substance that can't be broken down into simple substances by chemical reaction. He named or discovered or recognized most modern elements like oxygen, sulfur, hydrogen, phosphorus, and so on. He was able to distinguish metals from non-metals. So he put things on a basis that we already know in terms of modern knowledge. Most important contribution of his is this conservation of mass. He debunked the Phlogiston theory, was able to establish the metric system, which even today, for example, the United States has difficulty in accepting it. So already in the 1700s, Lavoisier introduced in France first extensive list of elements, came up with a chemical nomenclature. Most importantly was his obsession in converting chemistry from a qualitative science to a quantitative one. He was obsessed with precision, taking weights of everything and so on. So, a little bit of life of Lavoisier. He was born in 1743. He was a wealthy person, born into a well-to-do family, married into an extremely well-to-do family. So there was absolutely nothing in terms of him. He never knew what poverty was. Studied these subjects: chemistry, botany, astronomy, law, geology. Already knew that science had a very practical aspect to it. So he played a very important role, for example, in how street lighting could be there in Paris by gas, could purify water so that Parisians could enjoy water that is much purer, for example, than other parts of Europe. And of course was elected to the Academy of Sciences, and as I mentioned already, his wife Marianne played an extremely important role in his research, particularly in documenting and very carefully documenting all the apparatus that Lavoisier used. And that artwork, for example, today is preserved in the museums in Paris. So, I have shown that this is a movie that I borrowed from YouTube about how Lavoisier found the conservation of mass.
Monsieur, it is my great ambition to demonstrate that nature is a closed system, that in any transformation, no amount of matter, no mass, is ever lost, and none is gained. This precise amount of water is heated to steam. This steam is brought into contact with a red-hot iron barrel embedded in the coals. From this steam, we cool the steam. But interestingly, we collect less water than we started with. So clearly, we lose a certain amount of water. However, we also collect the gas, and the weight of the iron barrel increases. Now, when we combine these two increases, the new weight of the iron barrel and the gas we have collected, they are exactly equal to the weight of the lost water.
But is it atmospheric air, Monsieur Lavoisier?
Well, because I am measuring it to the very last grain, I can see that it is lighter than the air around us, and moreover, it is feminine. Wow.
Water is made out of hydrogen and oxygen. So what they've done is get the oxygen to stick to the inside of a red-hot iron rifle barrel. He was basically just making rust, which is oxygen and iron, but he was making the rust really quickly. Now that left the hydrogen, what he called combustible air, and then just floating around as a gas. No mass had been lost, it had merely been transformed. And now, he wanted to transform it all back into water.
This is what I'm going to do. In the next few months, I'm going to demonstrate that I can recombine this combustible air with vital air and transform them both back into water. I will recreate exactly the same amount of water that was lost here in this process. It is my hope to complete the cycle, water into gas, into water. Another job lost.
For a long time, Lavoisier has suspected that the exact amount of matter, the mass, involved in any transformation is always conserved. But to prove this, he had to perform thousands of experiments, and he had to do the measurements with incredible accuracy. That's where his great wealth from being a tax collector came in. He could afford to commission the most sensitive instruments ever built. He became obsessed with accuracy.
I suppose this persecutor of yours.
For years, Lavoisier burned, chopped, melted, and boiled every conceivable substance. They've shown that as long as one is scrupulous about collecting all the vapors, liquids, and powders created in a transformation, then mass is not decreased. Liquids might become gases, metals may rust, wood may become ash and smoke. The tiny atoms that make up all substances, none of it is ever lost. The crowning glory of this opus was their remarkable use of static electricity to cause oxygen and hydrogen to recombine back into water.
Okay, so you can see that by this absolutely brilliant experimentation, Lavoisier was able to now come up with a list of elements. And you have these that he has listed out, simple combustible substances and what he called earths. That's how we get the name alkaline earths and so on, and alkalis. And also he made errors. He, for example, got light and heated elements and so on. But he had the first list of elements that actually any scientist had ever made, and came up with this list in his treatise on chemistry. So what was established by this time by Lavoisier and others, that air was not a single element, fire was a process, not an element, water is a combination of elements, earth, many substances and combination of elements. Now I have to take you through some personal life of Lavoisier because it's interesting and tragic. Now Lavoisier was, as I told you, a very rich person. He was associated with a tax company called the Ferme générale. Now this was a company, very interesting concept. The state would get advance tax from this company, and in return this company would have the right to collect taxes. So the state would not have to worry about collecting taxes from individuals or firms, and they would, the firm would estimate the approximate tax in a year that the state is likely to get and would pay them in advance and collect. So Lavoisier was, being a very precise person, devised a foolproof method of collecting taxes, including building a wall around Paris. Now we hear about a lot of walls now. So a wall around Paris at the time, and actually had a method which was extremely beneficial for his company, but naturally made him a really hated person in Paris. And also, Ferme générale, a side story, but it is related, had a monopoly on the import of tobacco. And it was found that the tobacco that was coming in, unscrupulous elements, of course, are present everywhere in Europe too. And so they adulterated tobacco with various ways, including ash and water. And Lavoisier was given this task of how to detect this. He did. But he also found out by his experimentation that if you deliberately add a certain percentage of water, turns out 6.3% of water, you actually improve the quality of tobacco. So the company, by his advice, took his advice, brought clean, pure tobacco, added water, and sold to customers. Now, of course, it must be mentioned that they did not charge for the water, they only charged for the tobacco. During this time, of course, the French Revolution had started. You had 1789 to 19, the decade of French Revolution. Obviously, the first thing to be abolished was the Ferme générale. All the tax farmers, those of them who worked for the company were called tax farmers, they were all arrested. And Lavoisier was also charged. The charges on Lavoisier was that he defrauded the state because he sold, or because of his direction, the company sold adulterated tobacco, which was mixed with water. And of course, there was a quick trial. He was convicted and guillotined in 1794. And the judge was listening to the defense lawyer that here is a person who was a very famous person, had contributed a lot to science, and so on. But the judge said the Republic has no need of scientists or chemists. The course of justice cannot be delayed. I'm a little worried current events that, if not to that extremity, we are probably hearing similar type of statements. Now, this was a guillotine, a prototype of a guillotine that is there. I'm sure that this is there in one of the French museums still. It's a very quick thing. It's, the head is chopped off in a second, or perhaps less. So, of course, several people did regret this, like the mathematician Lothar Meyer said that it took them only an instant to cut off his head, and 100 years might not suffice to reproduce its life. Now, ironically, a year and a half later, the state realized that its charges on Lavoisier were perhaps not correct, so he was exonerated, and his possessions were returned back to his widow, saying that to the widow of Lavoisier who was falsely convicted. Now the story actually has a silver lining. One of the pupils of Lavoisier was Dupont, and Dupont escaped Paris during that time and went to USA and set up a company which was by a $36,000 company, and of course today it's a $25.8 billion company, one of the largest chemical companies. So in a sense, therefore, Lavoisier's work survives in the form of this chemical company. And this is Lavoisier's laboratory, so if some of you have occasion to go to Paris, apart from Louvre and other attractions, do take time to also visit the laboratory, which is preserved in one of the museums there. So we now move to the next person. I think it will be very brief. This is John Dalton. So by the time Dalton arrived on the scene, already all of this information was there. And Dalton, by several experiments and also intuition, could make this very bold sort of statements that elements are made up of extremely small particles called atoms, and atoms means non-divisible. And he actually also gave the first sort of representations. So this table you can't read it properly. So each one of them, this is for example hydrogen, this is nitrogen and so on. And he started to build what today would look like chemical formula in a chem draw picture that we would draw. So he started to build structures around this. And he of course also said that in chemical reactions, atoms are combined, separated or rearranged and so on. And Dalton gave a very firm sort of hypothesis in terms of how chemical reactions can occur. Now, during this time, again, England, of course, was at the center of things, both in terms of industrial revolution and science. And they had this fantastic tradition that a scientist would get a celebrity status. So you have this Royal Society exhibitory talks where the scientists would give a talk, charge money for it, and people would come buy tickets like it was a theatre and see experiments in science. So Humphrey Davy, who was at that particular point of time, started off in a very humble career, but by use of electrolysis, by use of the galvanic cell which was just invented, this is a galvanic pipe where you have zinc and copper alternating, and between you have an electrolyte. So discovered a number of elements by electrolysis. He discovered sodium, he discovered potassium, barium, calcium, strontium, magnesium, boron, and so on in a flurry. So every year there will be one or more element discovered. So this is a typical sort of what would have been at that particular point of time such a lecture story. You would see the demonstrator. Here this is the demonstration of the laughing gas, where a person would be called, a volunteer would be called, and would be asked to inhale laughing gas, and the effects of it the audience can see. And this was Humphrey Davy working as an assistant to this more established person. So Davy's contribution was, suddenly you had a large number of elements which were not known, all of a sudden now known. So people started to worry now. There may be about 30 to 40 elements known. Each one of these, is it unique or is there a relationship between them? That is basically where we come to today's story. So is there a relationship with all of these elements, or do we, for example, every element is separate? Now these efforts have culminated in many such organizations. So there was this by Newlands who had this brainwave that just as you have the octaves in music, perhaps you can organize elements in sevens, and the eighth element would have properties similar to the first element and so on. You had people who were organized in triads, and also you had Lothar Meyer publishing a periodic table very similar to what Mendeleev had done. But this kind of brings us to the first chemistry conference ever held, and this was in Karlsruhe. So in Karlsruhe in 1860, you had the first international conference in chemistry, and borrowing on discoveries made by Berzelius and others, Cannizzaro read out a paper on atomic weights, although the most important one was also Avogadro, and this particular paper had a tremendous influence on the growth of chemistry since 1860. So that kind of brings us to today's hero, Mendeleev. So a little bit of a story on Mendeleev also. Mendeleev was born, unlike Lavoisier, in an extremely poor family in Siberia. He was the 17th child, the last child of his family, and his mother was very keen on educating him. So she spotted that this person had a scholastic talent, so wanted to get him educated. And Siberia was not very good with educational facilities, so the only good places in Russia were either to go to Moscow or St. Petersburg. So she took her young son and had a very arduous journey. There are different accounts. Some say they went by foot, some say they went by a mule, and so on. So I think a more reasonable would be some sort of a horse or a mule-drawn carriage over a 1500-mile journey, and went to Moscow. The Moscow University rejected him because they said that you are not what in Indian terminology called not local. So you are a non-local from Siberia, therefore you cannot be admitted in the university. So they said that every province you have to get admitted to the same place, and you can't otherwise get admitted. So she tried very hard. Then she tried St. Petersburg University. So finally, he got admitted in a place which was called a pedagogical institute. So this was an institute that would be training teachers. So he got admitted in this place so that, and he had to kind of give a bond that once he graduates, he will go out and train teachers. So he got this, but luckily in this place there was a professor who was a student of Liebig. So those of you, of course, who have known chemistry, Liebig is one of the really big names in chemistry, the ancient chemistry. We have the Liebig condensers, Liebig processes, and so on. And so this was good for Mendeleev because he learned a lot about the German chemistry system. And when he got an opportunity to go abroad on a fellowship, of course he went to Paris, he also went to Munich, he went to Heidelberg, and in Heidelberg he set up his own laboratory in his apartment. And he had the opportunity to work with Bunsen, Kirchhoff, Lothar Meyer, and he also attended the first chemistry congress in Karlsruhe. So things have to all gel together for a person to do things, and this was the gelling that Mendeleev had the opportunity to attend this conference, and which gave him first-hand knowledge in terms of atomic weights that Henrey had read out. So then he came back after all this exalted studies, came back. And like most of our PhD students today, found there's no job. So they came back and found that in spite of going to Paris, going to Germany, going everywhere, being with the topmost names, there wasn't a job available. So he did all kinds of jobs. So he thought there was a prize money if you write a book. So he very quickly wrote a handbook on organic chemistry, got a prize money, which allowed him to settle all his debts. Then he worked as a consultant to the government. The government was interested in finding out about taxing alcohol, vodka, and they wanted to find out the purity of alcohol and appointed Mendeleev. Now the salary was good, and more importantly, they also had the barrels of alcohol coming along with the salary. So you had therefore salary plus barrels of alcohol given to Mendeleev for his job, which was not unattractive. And he experimented with various water-alcohol ratios, and actually then did a PhD thesis. And the thesis title is on compounds of alcohol and water. So quite a good subject, I would say, for a person to do PhD. And then this is kind of not well established, although there are rumors that is he the person who kind of put in place the secret recipe of the vodka that is there in Russia. But this is perhaps more of a rumor than reality. So all of this, he was then appointed a professor. So he got a professorial position at the St. Petersburg University, a professor of pure chemistry. Then of course the people in the university told him that you have to teach inorganic chemistry. Mendeleev knew nothing about inorganic chemistry, and so they said, but you have to teach the students inorganic chemistry. But he had written a book on organic chemistry, but they said, no, this is what you have to do. And so he was searching for books on inorganic chemistry, found there were none in inorganic chemistry. So he decided, okay, I will write my own book on inorganic chemistry and start off the course. So since there were no textbooks, and since he was asked to teach inorganic chemistry, he decides to write his own book. So the book, he had a plan for a book with what was known. So he said, okay, there is hydrogen, oxygen, nitrogen, carbon. So he called them organogens. Then there were other books, halogens. We knew what halogens would do, what alkali metals would do. But he very quickly got stuck if this is the way I'm going to teach chemistry, then it perhaps is not going to be the most interesting way, because every element I cannot describe it under a separate chapter, sodium, potassium separately. Is there any commonality between these various collection of elements? And this is basically where he started to look at the commonalities. And then he found that as he was writing this book and organizing these elements, that if you go to lithium, and these were the atomic weights that were available at the time. So he organized them in atomic weights. You take lithium and then you have sodium and potassium. There is a relationship of the fact that sodium is 16 units more than lithium, potassium is 16 units more than sodium, and they seem to have some sort of a relationship in terms of properties. Similarly, beryllium, magnesium, calcium, boron, aluminum, carbon, silicon, oxygen, sulfur, and so on. So he was intrigued by similarity. No, he was not the first person to search for similarities. There were, as I told you, other people who were searching for similarities. Then he actually started to write this thing. This is a draft periodic table, and you can see, like any one of us, he puts down everything, scratches things out, writes things in, and so on. And you can see this is like work in progress, things that are happening from Mendeleev's periodic table. And finally, he does come up with this periodic table that I had mentioned earlier in 1869, and now this is the page number and the volume of this Zeitschrift for Chemie, and this of course exposes Mendeleev's work suddenly to the world, so to speak, the world being Europe. So you have the periodic table known, and of course Lothar Meyer, who had published this a couple of years later. Then Mendeleev also realized that what he was simultaneously trying to figure out was also discovered or published by Mendeleev. So Mendeleev here, you can see what he does is, this is, as I told you, organized slightly differently than what we are used to. So we have carbon, silicon, then there is something missing, then there is tin, and you have boron, aluminum, something missing, then there are and so on. So you have fluorine, chlorine, something missing, puts J, and he writes of course on what basis he has come up with this, which we now know, but I'll just to complete the story. What he said was the elements, if arranged according to their atomic mass, exhibit an accordant periodicity of properties. So this was an important postulate, which of course we know is incorrect today, but this was the basis of his organization. And the elements which are most widely diffused in the universe have small atomic weights. This is remarkably correct, remarkably prescient. We must expect discovery of many yet unknown elements such as Eka, aluminum, and so on. And indeed, this Eka comes from Sanskrit. So again, I think there will be some cheers, at least in some quarters, that in Russia you had older Russians knew Sanskrit and used it, and he had a Sanskrit influence and therefore used Eka aluminum, Eka silicon, and so on. And he also had actually the boldness to kind of write down the properties of those. So he said that this is not yet discovered germanium, this is going to be its density, this is going to be its melting point, and so on. And then he also said that the magnitude of the atomic weight determines the character of the element. So I think this is basically what distinguishes him from other people at that time who had tried to organize elements or tried to find out relationships. By 1871, you can already see things in form that we kind of can be used to. You have this, you have lithium, potassium, sodium, and so on, and you have boron and carbon and so on, silicon. There are missing elements with these atomic weights and whose properties he had predicted. And he also had iron, cobalt, nickel. He also knew metals with the organized triads. So he kind of already had a hunch about most of the things, and most of the things he did come out quite correctly. While this was happening, during experimentation by Lord Rayleigh and Sir William Ramsay, they found out that they had a new gas, and this gas was argon. Okay. And they could not put it in the periodic table of Mendeleev. They said that where does this fit in? So of course Mendeleev did not have an answer at that time. It had an atomic weight 39.9 as calculated then. So obviously it has to come after potassium, but it is not possible. possible because potassium already has a valency of 1, so that means argon should have a valency of 2, so that's not possible because it doesn't react. Luckily, very quickly other family members of this group were discovered with very similar properties. So Mendeleev very boldly went ahead and put another column and said that these are the 0 group elements and said that these are separate column and called them group 0. So he kind of indicated already the flexibility that the periodic table could have, and by putting new undiscovered elements in various slots. So by the time 1900s, actually there was no question that Mendeleev's periodic table already had played a very, very important role. So it was natural that people would nominate him for the Nobel Prize, and let's see what happened. So he was nominated twice, 1905 and 1906, and apparently the way the Nobel Prizes work is that there is a committee which first recommends, and then it goes to the final academy, and usually the committee recommendations are accepted. So 1906, the chemistry prize was recommended for Mendeleev, but there was a dissenting member who proposed the name of Henrey Mosely for discovery of fluorine, and there was a colleague, very famous person, Arrhenius, who was in the Swedish Academy, who for a variety of reasons was completely anti-Mendeleev, particularly because I think Mendeleev had criticized some of his laws of electrolysis and so on. So he made sure that Mendeleev did not get the prize and Mosely was given the prize. And this is documented in several books and several things. And unfortunately in 1907 he could have been nominated, but he died. So of course you can't get the Nobel Prize if you die. So the very interesting book on this aspect is the periodic table in the West Nobel Prize by Ulf Lagerquist. He himself was a member of Nobel Committee, so he knew, he knows how things work. So and incidentally, the Nobel nominations are not revealed to the public. I think 50 years have to pass by since the first nomination, and then only they are revealed to the public. So all the nomination papers we can access now of the older Nobel Prizes. Okay. Now very quickly, now we have this periodic table in place, and 1900 to 1930, of course, the golden period of science. And those of you who have not read this book, I strongly suggest you to read this, The 30 Years That Shook Physics by George Gamow. I think it's an absolute must read for any science practitioner in terms of how science progressed and so dramatically in the 1900s. Apparently, in those days, we don't get Nobel Prize by 29 or 30, you would have a big psychological problem and you would see a psychologist, because by 30, if you haven't done anything, it's like your life is not worth pursuing. So during this time, number of things had happened. For example, radioactive elements were discovered, polonium, radium. The place in the periodic table was not clear. Also, the question of atomic weights being the basis of this, elements was also being questioned because isotopes were now discovered. So you had by Soddy and other people, isotopes were discovered. So you know that same elements had different weights. So is atomic weight the guiding principle of periodicity? So this question was already coming into the picture already in 1900s. Now this person, again somewhat of a tragic story, a brilliant person, Henrey Mosely, a student of Rutherford, but did not want to pursue the same work that Rutherford was doing. So he was working not at Manchester but at Oxford, and but had a mentorship. He was mentored by Rutherford. So he found out that the X-ray wavelength of an element and its atomic number are that there is a relationship between the two, and he was able to resequence the entire periodic table by nuclear charge rather than atomic weight. Now prior to this also the elements had numbers, but they were just sequential numbers. People just put 1, 2, 3, 4 without realizing what those 1, 2, 3, 4 meant. But Moseley was the one who showed that these were not sequential numbers, they had a meaning. And indeed, the periodicity is a natural law rather than something that is arbitrary organization of information. So, for example, now argon with an atomic number 18, although has an atomic weight 99.9, has to come before potassium because potassium has an atomic number 19. So it comes and fits in absolutely beautifully and naturally. And similarly, cobalt comes before nickel, tellurium before iron. So all these are puzzles before Moseley's discovery. And also the elements with atomic numbers 43, 16 were unknown and had to be formed and so on. So Moseley was doing absolutely brilliantly in his career, but he was drafted into World War I and had to in Turkey, where a sniper's bullet killed him. And as a consequence of that, Rutherford and other people in England had, I think, strongly petitioned to the British government. And I think since then, certain categories of people can't be drafted into war. So this was the periodic table, almost the 1930s, which has a very strong resemblance to today's periodic table. You can see lithium, sodium, potassium, rubidium, cesium. And of course, at that time, the periodic tables were 1A and 1B, because lithium has got class 1, so can copper 1, silver 1, and gold 1. Therefore, that is 1B. But people realize there is a difference between 1A and 1B. Okay. Similarly, you have 2A, 2B, 3A, 3B, and so on. So by 1940, which is already the modern era, you have the periodic table very nearly in the current form. There were gaps. These gaps are very quickly found out: magnesium, promethium, astatine, francium. But now the gaps were such that, unlike in Mendeleev's time, where he with different atomic, he said that this had to be there. Now there was more certainty that if you had a gap to the atomic number, meant it had to be formed. We come to the really modern era, because Glenn Seaborg was actually the advisor to many modern US presidents, including Kennedy and later on. So he, by now nuclear reactions, by the new technology that became available post World War II, discovered number of elements, almost like Henry Cameron. I mean, like the previous person that I discussed, he discovered now plutonium, berkelium, californium, Einsteinium, and was the element 106 was named after his Seaborgium, and you can see him standing next to the periodic table with the element symbol Sg there. So perhaps he is the only person who could do this, standing next to the periodic table and pointing to an element which bears his name. And of course, these are created by these nuclear reactions. And indeed, Seaborg finally realized this ancient dream of alchemists of converting something to gold. So Seaborg did convert bismuth into gold by nuclear reaction and published this in Physical Review C in 1981. Except that he said that this would cost more than $1 quadrillion per ounce to produce gold by this experiment. So the going rate for an ounce was about $560. So clearly, although this was done, our ancient alchemists would not have been too pleased about it. So if you want to read about this, this is in the Scientific American, which tells in a more sort of a layman's language about the experiment, which consists of taking carbon and neon nuclei and slamming them into foils of bismuth. Then they discover the gold 199 is formed in such reactions. Okay. What next? So we have this now periodic table, and I must also mention that Seaborg was the person who found this place for lanthanides and actinides as separate periods, and you have therefore separate columns below the periodic table, their place established. So what is next? Of course, lots of elements do get discovered in such nuclear reactions. So there are a lot of theoretical studies. One of them is by Pekka, who has an extended periodic table which was published by him, which includes elements with not just f orbitals but also with g orbitals, and he says that up to 172 if you have elements that you can have a periodic table like this. So I think that's all. I leave you here, and the material that I had borrowed was from various sources. Mendeleev Communications. So there's a journal called the Mendeleev Communications, a very prestigious journal. And also from Wikipedia and the books that I cited. I must also mention YouTube over here. And no students' names appear here because this was the first PPT that I prepared without the help of any of my students. So thank you very much for your attention.